So we're going to do a little bit of review. Let's take a look at this review sheet. Oops, wrong button. Too many screens. All right, so we'll come back to some of the questions in number one. Let's take a look at number two here. So a little history on where number two comes from. If you consider f of x equals x squared minus 2, we know that to find a root of this, we would set it equal to 0. That gives us x squared equals 2, or x equals plus or minus the square root of 2. Now, that's all well and good, but a long time ago, how did people determine what the value of the square root of 2 was? We needed a way to approximate it. So Newton came up with a way to do this using calculus. And the way he looked at it, this function has 2 roots. So it looks something like that right there, to the best of my artistic ability. And what Newton said is, well, just make a guess. So make believe I'm zoomed in here. Make a guess at that root. So maybe that's our guess right there. And then we calculate what f of x is, and we see, oh, it's not 0. We missed. So then what we do is we find the tangent line through that point. And what happens is when we do that, the 0 of the tangent line is going to be closer than our guess. And so we use this value as our new guess. And we plug it into the function, and we get a point, and then we find that tangent line. And that tangent line, guess what? Is going to be even closer than guess number 2. So we had guess number 0, guess number 1, and then in there we have guess number 2. And if you repeat that process over and over again, what you get is the following sequence, that given some initial guess, that the next guess is going to be equal to 2 divided by the first guess plus the first guess over 2. And one way to think about this right here is this here I'm taking my previous guess, I'm dividing it into 2. All right. What happens then is I get a pair of numbers here and here whose product is 2. And then I'm averaging them, which means I'm finding a number in the middle. And so if one of these overshoots the square root of 2, this one has to undershoot it. Okay, so for example, if I take a guess to be 1, then my second guess, well, what would, if you take 1, you divide it into 2, you get 2, right? And would you agree that 1 times 2 times 1 is 2? So the product of these two numbers is 2. I'm averaging them to get a new better guess. My new better guess, oops, I'm still on the second one, is now 1.5. Okay, so is 1.5 the square root of 2? Well, there's one way to check. If I take 1.5 and I divide it into 2, well, what's that going to give me? Let's see, that's 3/2, so that's going to give me 4/3, which is 1 1/3. Okay, that undershoots square root of 2. This one overshot the square root of 2. But now if I average those two, 1.5 plus 1 1/3, and divide by 2, I'm now slightly closer than I was before. And so if I just whip that out on a calculator, because it's getting kind of tedious, 1.5 plus 1 1/3 divided by 2, I get 1.416, which is already pretty darn close to the square root of 2. So Newton's method using linear approximations with tangent lines zooms in quickly. All right, so that's where the sequence comes from. And so if you didn't recognize that first, you'd quickly see after plugging in a few numbers that the sequence quickly converges to the square root of 2. But how do we prove it? Because just numerical examples isn't enough to prove it. So here's the way we prove it. So we believe that the following sequence, defined recursively like this, we believe that this converges. So the limit, n gets big of a sub n, we believe that that has a limit. Now, would you agree that, you know, when I move on down the line, I have A0 and then there's A1 and then there's A2 and then way down here, there's going to be something called an A sub n. Right before A sub n is A sub n minus 1. As n gets big, these two guys are just moving down the line together. So if we say A sub n has a limit, well, its partners go into infinity with it. And so that means it's also true that the limit as n gets big, that was supposed to be an infinity right there, of A sub n minus 1, that has to go to L too. Doesn't matter whether we call it n or n minus 1, as n gets big, they're both heading to the same spot. So what I have is a means of substitution. I know that A sub n is going to L in the limit. I also know that A sub n minus 1 is going to L in the limit. So if I take the limit of both sides of this equation, then what I get is the following. I get that L, the limit on the left, has to equal 2 over L plus L over 2. Because both A sub n and A sub n minus 1 are heading to L. So I just replaced them all with L. So I'm taking the limit on the left, take the limit on the right. Then we just solve this algebraically to see what values of L make this true. Let's do it. Solving this, I would multiply the 2 to the other side. So I get 2L equals 2 over L plus L. That L in the denominator is kind of a pain in the butt. So I think I'll multiply both sides by L to get rid of it. So then I get 2L squared is equal to 2 plus L squared. And let's see, I guess I should bring the L's all to one side by subtracting. So I get L squared equals 2. And so L is either plus or minus the square root of 2. Question, does this last section right there look kind of familiar? That was my premise for the problem. I didn't give you where I got the problem, so it's hard to notice, but once you get to the end, you're like, oh, wait, that's Newton's method for coming up with that answer. So we can look at it in a couple of different directions, but this shows us that, yeah, numerically it looks like it's going to the square root of 2, and now we can show that in the limit it's got to go to the square root of 2. Now it could go to the opposite of the square root of 2 if I had done something like if I picked oops, that's not a marker. If I had picked there we go. If I had picked A sub 0 to be something like -1 as the starting guess, then that would lead me in the limit to negative square root of 2. Okay. But on this problem, I believe I chose A sub, what did I pick? I picked A sub 1 to be 1, which is going to take us to the positive square root of 2. Then the proof of this is this part right here, that we believe that there is a limit for the nth term, which means the nth minus 1 term has to have the same limit. And then by substitution, we can algebraically show that's the limit. And that can be applied to a lot of different recursive functions. So pretty much anytime you have a recursive definition, you could apply that and you should come up with something, either convergent or divergent, and what it converges to, which is kind of nice. I should be able to do that with H. Yeah. Now H, you can pretty much see numerically that it's going to diverge. You're just going to bounce back and forth between 2 and 3, 2 and 3, 2 and 3. So that one's pretty straightforward. So we wouldn't need to. But let's take a look at G. G is kind of interesting. Let me make sure I got it right. Yep. Okay. We did one like this in class a long time ago. So I've got A sub n equals 1 plus 1 over n to the power negative n. And let's see, that's all I need here. So I want to figure out what's happening with the limit here. So what is the limit as n gets large of 1 plus 1 over n to the power negative n? And the problem here is if I sneak infinity into this, I probably want to rewrite it to get rid of that negative exponent there. So let me do that first. Limit as n increases of 1 over 1 plus 1 over n to the n. And if I sneak the infinity in, it looks like this guy goes to 0, so this is 1. So it looks like I have 1 to the power infinity. And we might want to say, hey, 1 to any power is 1. But infinity is a sneaky character. And so we got to be careful about that. This is an indeterminate form. Okay, so 1 to the power infinity is a sneaky sucker like infinity over infinity. We're never quite sure what we're doing until we do a little more exploration. So it might be a good idea to plug in some numbers for n and see what happens. So I'm going to whip out the Desmos sequence grapher, which I have linked here somewhere. There we go. And so my sequence is parentheses 1 plus, and let's see, do I have to use a capital N here? I think so. 1 over capital N raised to the power negative n. And looking at the first, 66 terms here, it does not appear to be going to 1. 1's up here. It's going to something down here. So let's go out and grab 100 terms and then see where we're at. Yeah, definitely not going to 1. Okay, so the indeterminate form is haunting us. It comes out to something like 0.37-ish. 0.37-ish. I don't recognize that number. You guys? Not off the top of our heads. Okay, so it's a little bigger than 1/3. Okay. All right, well, let's see where it goes. So we got to do something else. So we got a couple of different options. We can't really apply L'Hopital's rule here because it's not 0 over 0, infinity over infinity. So we believe that this has a limit, right? Yeah. So let's go with that, kind of like before, but slightly different. So we're going to say there is a limit as n increases of a sub n, and it is L. So comparing that to this guy here, I believe that L is equal to the limit as n increases of 1 over 1 plus 1 over n to the power n. Problem, I have the variable in the base and the variable in a power. What could help me separate those? What tricks do we have algebraically to separate a base from its power? Logarithms, excellent. Yeah, so we're going to apply a natural log to each side here. So I'm going to take the natural log of this side, and I'm going to take the natural log of this side. So let's see. Well, natural logarithm has that property that I can pull it through, or sorry, limits have the property that if the limit exists, I can pull a function through the limit or the limit through a function. So rewriting this, this is going to be the same thing, new page, there you are, as the limit as n increases of the natural log of 1 over 1 plus 1 over n to the power n. All right, now properties of the natural log. Natural log can take a quotient like this and separate it into a subtraction. So then I'm going to get the limit as n increases, and I'm going to put some brackets outside this, of the natural log of 1 minus the natural log of 1 plus 1 over n to the power n. So these parentheses here are for the limit because the limit applies to the whole difference. Okay, can we clean this up a little bit? Well, the natural log of 1, what's that? 0, okay, so that's nice. And then the natural log has that property that powers come out as multiples. So now I'm going to pull out the negative sign. Limit as n increases. So I grabbed that negative, pulled it out, of n times the natural log of 1 plus 1 over n. Okay, so what's happening here? Well, let's see. As n gets big, this is going to give me an infinity multiple on the outside. Over here, 1 over n goes to 0, so that means I have the natural log of 1, which is 0, so I have infinity times 0, indeterminate. Okay, trick. Well, I'm going to rewrite this instead of multiplying by n. Guess what I'm going to do? Divide by 1 over n. So my belief is this is the same thing as the opposite of the limit as n gets big of natural log of 1 plus 1 over n over 1 over n. Okay, how does that help me? What's the top going to? 0. What's the bottom going to? 0. Okay, 0 over 0. I can finally use L'Hopital's rule. So we just had to do a ton of algebra to try and get it to a point where we can tweak it with some serious calculus like L'Hopital's rule. So L'Hopital's rule, that's a fancy L, believe it or not, says take the derivative of the top separately from the derivative of the bottom. So let's see, that's going to be fun. Derivative of the natural log is 1 over whatever's inside. So my numerator here is going to have a 1 over 1 plus 1 over n times the derivative of what was inside. Okay, well, the derivative of 1 is 0. What's the derivative of 1 over n? Negative 1 over n squared. Yep, so I'm going to have a negative 1 over n squared. Ooh, that's kind of nice. What's the derivative of the bottom? Negative 1 over n squared. Oh, this is so cool when things start to get rid of themselves. So those guys divide out. Uh-oh, my pen's freaking out. There we go. So these guys divide out. So now I have the limit as n gets big of 1 over 1 plus 1 over n. Just this sucker right there. And oh, don't forget I have that negative sitting out front. Let's throw you up here for now. I'm running out of room. Well, what's this go to? Negative 1, right? Okay, negative 1. But go back a page. What we just calculated is the natural log of our limit, not our limit. So here's where we are now. New page. We know now that the natural log of our limit is equal to negative 1. Well, natural log is base e, so that means e to the power negative 1 has to be our limit. And let's see, e is just a little smaller than 3. And now I have the reciprocal of e, which should be a little bigger than 1/3, which is where we were headed. Let's double check. So what is 1 over e? It is 0.36789, blah, blah, blah. Cool. Double check. Let's plug in a big N. If I go and plug in 1 plus 1 over 1,000, close parentheses, raised to the negative 1,000, I should get relatively close to 1 over e. It's not super fast growing, but it's not too bad. Whew, that was exciting, huh? Yeah. It just like something like E or pi or yeah, I know. Those come up a lot. I have a whole book of cute limit sequences and series related to E and pi. And all right, let's try another problem. And then that was quite a bit of algebra. Yeah, that was. So, well, I did and I didn't. So I put it in a section where I said, do 5 of these guys, right? So I give you an out. Like that's a pretty tough one right there. And earlier I had this one in that group up there and I decided to pull it out separate just to give an extra challenge. All right, so with that in mind, let's go back and look at F here. All right, so because that's going to lead to another indeterminate form, which may or may not lead to something like E. All right, so F said, take the limit as n gets big of the nth root. What was that again? N minus 1 over n. N minus 1 over n. So rewriting this sucker, I have the limit as n gets big of n minus 1 over n to the power 1 over n. And just for fun, I'm going to rewrite it one more time because a lot of times what I do and I don't know what to do is I just screw around with algebra and hope something will jump out at me. I could rewrite this fraction here as n over n minus 1 over n, which is 1 minus 1 over n to the power 1 over n. And now it's starting to kind of look like G, but not quite. So if I try to cheat here, what happens is I'm going to get 1 as the base, and then I'm going to get 0 as the power. And is it safe to say 1 to the power 0 is really 1? Maybe. Okay, it kind of depends on the growth rate. So what we're going to do is just look at this numerically and see if it looks like it settles down. So where is that bugger here? Let's see, go away, go away. Okay, so this time we have a 1 minus, and in the power we have a 1 over n. Oops, and delete that sucker. Okay, and this one does look like it's going to 1. So it may be just as straightforward as you were thinking. Yeah, looks like it's going to 1. Okay, so let's test it out. So just to be sure, this seems to be pointing to 1 to the power 0, which could likely be 1. And our numerically, it looks like that's the case. So just to double check, what we're going to do is say, okay, we know this thing has a limit. So it's equal to L. And then we're going to separate the power with a natural log. So the natural log of our limit has to be equal to the limit as n increases of the natural log of 1 minus 1 over n to the power 1 over n. Okay, so I can rewrite that as the limit as n increases of 1 over n times the natural log of 1 minus 1 over n. All right, so what's happening here? Well, let's see. The front term, 1 over n, that's just going to 0. And this guy right here, what's it doing? It's going to 0 too. Okay, so there's no 0 fighting infinity here. They're both saying, hey, let's go to 0 and multiply, which means they're going to go to 0 faster. So hey, this whole thing is going to 0. So we now have the natural log of our limit is equal to 0, which translates as e to the power 0 is our limit. And so yeah, our limit is 1. Okay, so we have pretty good intuition here by trying to plug in infinity. Using natural logarithms with the limit, we still get the same result. We also have numerical evidence, so I think we have pretty good conclusion here that, yep, it's 1. All right, next, let's take a look at, where did that sucker go? Over here. I think the rest of these limits weren't too bad. They were pretty straightforward. How about these series here? These weren't too bad, were they? Any of you got stuck on there? Okay, well, I'll give you some time to do some more. Kezia, what did you have any trouble with any of those? J, oh, that's a cute one. Let's take a look at J. All right, and that kind of fits in with what I was hoping to get to today also. So new page. So where am I starting that sum at? N equals 1 or 0? Okay, so n equals 1 to infinity, n plus 1 over n factorial. So anytime I have a factorial, I think ratio test. Okay, so if I apply the ratio test to this, then I'm going to get, so usually I don't write limit right away, I just plug in n plus 1. So that's going to give me an n plus 1 or an n plus 2 over n plus 1 factorial times the reciprocal instead of dividing, which is n factorial over n plus 1. Cleaning this up, usually when I have factorials, I write them out a little bit. So this is n plus 2 there times n factorial is n times n minus 1 all the way down to 3 times 2 times 1. N plus 1 factorial is n plus 1 times n minus 1 all the way down to 3 times 2 times 1, and then I have this other n minus 1 hanging out down there. And then the lovely thing about the ratio test and factorials is stuff starts getting annihilated, right? 3 times 2 times 1, all this stuff goes away. And I think I canceled everything I can. So I'm left with, in the numerator, an n plus 2, and in the denominator, an n plus 1 times an n plus 1, which I think I'm going to multiply that out just for fun. That would be n squared plus 2n plus 1. And what I'm concerned about here is now absolute value, all of these terms are positive, so that's no big deal, right? I need the limit of that thing as n gets big, of that ratio. Well, a quadratic function way outcompetes a linear function. So even though the top and bottom grow, the bottom grows faster. And so this is definitely going to 0. The ratio test says it needs it to be less than 1. Yep, 0 is definitely less than 1. So that implies convergence. And we might be able to discover its convergent value today. So I'm going to give you another day to work on this. Number 4 here, we proved its convergence when we did the section on the integral test, and the integral test has a remainder tool that you can use. So look back in your notes on that and give that a try. And then this one is an alternating series, and the alternating series has a remainder theorem to it also. So give those two a try, and then we can go over them in class together tomorrow. So I'm going to stop the review here and do some power series stuff. So the test that's coming up will have 3 parts to it. One part is just sequences, which is just taking limits. Part 2 is using all those different tests we came up with to determine if a sequence, a sum of numbers that's infinitely long, converges or not. But we don't know what it converges to most of the time. The third part is power series. That's when we throw a variable value in there, and we have whole ranges of numbers that we converge to, and we have functions that give us convergent values. So that means the power series stuff will tell us when what a lot of these guys converge to when they do converge. All right, so we're going to do a problem from section 9, and then if time permits, we're going to do let's see, a Taylor series problem. So homework 9, one of your classmates asked me about one of these. And oh, does anybody, if I didn't extend your homework, I will for 8 and 9. Do either of you guys need an extension on 8 or 9? You got it done, okay. I know, I did that on purpose. Yeah, because this one I asked a little bit more detail about. And then I did a problem just like this one in class Thursday. Yeah, on Thursday. So let's see, what did we calculate? We just had a different numerator, and I don't think we had 4 there, but maybe we did. Anyway, let's see. Oh, there's a nice one. -5 + 5, 0. Submit. All right. Oh, but it's in review mode for me. All right, which one did I want to do? Oh, I'm not seeing the one I wanted. Am I in the wrong section? Was it in section 8? Huh, maybe I'm in the wrong section. Let me check. Let's see, Haley asked me a question. Oh, it was section 8, number 13. Okay, that's the one I wanted to go over. I'm in the wrong section. Which one was it, 11? No. Did you guys notice which one she asked about? 13, okay. Oh yeah, that's a beauty right there. All right, so let's go over this one right here. This one's a wee bit complicated. I don't know if it gave you any fits. So it's not quite a factorial, but it's kind of close. And it turns out you can write things like this as factorials, but it's kind of messy. So I'm not going to worry about that right now. Time permitting, we'll do it later. So here I have the product of odd numbers. Here I have a product of even numbers. So let's copy that into my notebook and give it a shot. Oops, wrong button, screen. All right, so we want to find the interval of convergence of this right here. And to do that, we use the ratio test. And so ratio test says take the absolute value of the nth plus 1 version of this. So we just have to be careful replacing n with an n plus 1 in each spot. So my numerator of the first part is going to be 1 times 3 times 5, dot, 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 all the way up to, if I replace 2 with n plus 1, that'll give me 2n plus 2 minus 1, which means the next odd number is 2n plus 1. Okay, which kind of makes sense when you think about it, times x plus 7. And here, if I replace n with an n plus 1, I'll get 2n plus 3 when I clean that up, which is the next odd number after 2n plus 1. All right, so that's my numerator for the first part, divided by 2 times 4 times 6, all the way up to 2n plus 2. Okay, so this is my n plus 1th term. And then I want to multiply by the reciprocal of the nth term, which means just flip this guy right here. So that's going to be 2 times 4 times 6, dot, 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 all the way up, oops, not adding here, times 2n, divided by 1 times 3 times 5, all the way up to 2n minus 1. And then I'm going to have an x plus 7 to the power 2n plus 1. And all of that's in absolute value. All right, so then we get to cancel stuff, right? So the whole 1 times 3 times 5 cancels. Now, this one goes farther. What odd number is right before 2n plus 1? Two n minus 1, right? Because the term right before this guy right here would be 2n. That's even. Go back one more, 2n minus 1. So right before this guy was a 2n minus 1, and that's going to cancel all the way up to there for that run. All right, so here's 2n. What number is right after 2n? What whole number? It'd be 2n plus 1, right? But that's odd. So the next even number is 2n plus 2. So right before this guy is a 2n in the list. And so all those guys cancel. So we get a lot of cancellation here. And then here I have x plus 7 to the power of 2n plus 3. Over here is x plus 7 to the 2n plus 1. So altogether, we're going to have an x plus 7, and we're going to have this power minus that power. What's 2n plus 3 minus 2n plus 1? It'd just be 2. Yeah, this one is 2 more than that one. All right, so cleaning all of that up, I think this is what we have. I think we have a 2n plus 1 in the top. And then I think we have parentheses. I think we have an x plus 7 squared. In the denominator, I think I just have this 2n plus 2. And everything else got eliminated. All right. Nothing cancels here, so the best I can, I've canceled everything I could up there, so now I'm ready to take the limit as n gets large. Well, as n gets large, the only n's live right there, and those are both polynomials of the same degree, so that means the leading coefficients show where they go. So that means it goes to 2 over 2, which is really 1. So ultimately, this pen, come on, there you go, is equal to the absolute value of x plus 7 squared. All right, so let's see, x plus 7 squared, well, that's always positive, right? So that is actually just x plus 7 squared. And the ratio test says that sucker has to be less than 1. Now, that's a slight problem because I have a square. How do I get rid of the square? Right, take the square root of both sides. Now, if it was an equation, we would say x plus 7 equals plus or minus 1. But this isn't an equation, this is an inequality. So the intermediate step for an inequality, what is the square root of a square by definition? It is the absolute value. Yeah. So what I have then is the absolute value of x plus 7 has to be less than 1, which means x plus 7 has to be less than 1 or greater than negative 1. So like before, this gives us a center. If I rewrote that as x minus negative 7, then 7 is the center of my interval, and the 1 is the radius of my interval. So just to double check, if I were to solve this inequality, this compound inequality, I would subtract 7 from each side, and then so I'm going to get x is less than -6, and x is greater than -8. And if we look at that on a number line, here's -8, here's -6, open circle, shade. What number is exactly in the center? -7. And what's the distance to the edge? That's our radius. Yeah. So what we have is we have a radius of convergence of 1. Do we have the whole interval yet? Not yet. We have the interior of the interval, but we don't know what's happening at the endpoints, and so those need to be tested separately. Because the ratio test, well, that's not an 11, by the way. That's an absolute value of, let's see, let's put stuff inside of it to make it look better. Okay. We have to test the endpoints. So we have to see what's happening at x equals -8, what's happening at x equals -6. Ooh, that part's a bit challenging because we have a complicated thing right here. So let's grab that sucker. All right, so we first need to plug in, I don't know, let's plug in x equals -6, the right endpoint. So if we plug in a -6 here, oops, let's switch color. -6 and 7 is 1. This thing to the 1 is kind of boring, it's just 1. So that means I'm going to have here the sum as n equals 1 to infinity of 1 times 3 times 5 all the way up to 2n minus 1 divided by 2 times 4 times 6 all the way up to 2n. Interesting. It's kind of like factorial. Now, I can't apply the ratio test here because the ratio test will give me an answer of 1, which means it's inconclusive, and I need another test. What else could we apply to this? Ooh, I got an idea. Each of these guys is even, right? Okay. So let's see if this helps. So I can rewrite that denominator as, I can pull out a 2, a 2, a 2. How many 2's can I pull out? How many of them are there? Huh? N of them, yes. So there are n 2's. So I'm going to factor out all of those 2's. So in the denominator, I'm going to get a 2 to the n. And what is that going to leave behind? Well, it's going to leave behind a 1 times 2 times 3, all the way up to n. Okay, interesting. That's some of these guys up here, isn't it? Okay, so let's see. Eventually, there's going to be a 5 that's going to cancel with that 5. And let's see. Ooh, well, no, it's more complicated. That goes up to 2n minus 1. Darn. What's bigger, n or 2n minus 1? Well, 2n minus 1 is almost twice as big. Okay. I thought that would be more helpful. Interesting. One, 3, 5. So we're only going to cancel about half of these guys because n is somewhere in the middle here, and then we get up to 2n minus 1. That leaves us about where we were before, I think. All right, so what tests do we have at our disposal? Can't use the ratio test. That's out. There's no roots here, right? So the root test would not be helpful. What are the tests that we use? Integral test. How the heck do you take the integral of something that looks like a factorial? You'll get to that in some further math course. Can't use that. It's not alternating, so that's out. How about the divergence theorem? We haven't tried that. Divergence theorem says, forget about the sum, just look at the limit as n increases of the individual terms. What's happening to 1 times 3 times 5 all the way up to 2n minus 1 over 2 times 4 times 6 all the way up to 2n? Well, let's see. 2 is greater than 1, and sorry, yeah, 2 is greater than 1, 4 is greater than 3, 6 is greater than 5. Is 2n greater than 2n minus 1? Okay, so the denominator seems to be bigger than the numerator. So this right here is a proper fraction all the time. So what do we know if it's a proper fraction all the time? What's it got to be less than? 1. Got to be less than 1. So that tells us it's bounded. All right. We had a theorem about sequences that says if it's also monotonic, meaning strictly increasing or strictly decreasing, then there's a limit. Okay, so let's see, how would we show that it's strictly increasing or strictly decreasing? We would have to show the n plus 1th term is always, say, less than the nth term. That might be possible. Looks like we're not going to have time for 10-10 today. So let's see. What do these guys look like? Well, the first term is 1 over 2. Second term is 1 over 2 times, 3 over 4. The third term is 1 over 2 times 3 over 4 times 5 over 6. So I think it's relatively straightforward to look at this and see that it's decreasing, because each time we multiply by a number less than 1, which is going to be smaller than the previous term was. Okay, so it's decreasing and it is bounded. Therefore, there is a limit. What's a candidate for that limit, do you think? 1, 0, something in between? You like 1? So since this is going to be a tough one to do because we don't have an algebraic formula that Desmos will like. And so I think the only way to do this is maybe with a spreadsheet. So let's go whip out a spreadsheet. How about Drive, sheets. So let's go math classes 253. And this is a homework problem, new sheet. Okay, so how am I going to tell the computer to do this? I need to generate even numbers and odd numbers, and then I need to divide them. So let's see, numerator is odd, right? So 1, 3, denominator is even, 2, 4. And we need to extend both of these. Okay. Then we want that as a quotient. Call it ratio, it's easier to spell. And so we just take this guy divided by that guy. All right. Okay, so that's each successive multiple. So then we have to start multiplying these together. So at first, we just have this guy. And then after that, so this is now our product of these successive ratios. So then we just take the previous product and multiply by the next ratio. And these should be my terms of the sequence. Ooh, it looks like it's going to go to 0. I thought it was going to go to 1. Did I do that right? Let's see, this one right here, let's pick on this guy right here. No, let's go in the middle. That should be equal to 1/2 times 3/4 times 5/6 times 7/8. Oops, I missed something. 7/8. I want you to type a 7. Oh, the 7 key is stuck. Somebody must have spilled something or on the keyboard. Is that the right number? Yep. Okay, so it looks like I'm calculating those products right. So let's go for 100 terms. Okay, so here are the first 100 terms. I don't know. It's definitely decreasing. But is it decreasing to 0? I don't know yet. To be continued. We're out of time. All right, so sometimes even sequences, the easiest thing we've done in this chapter, can get us stuck. So do we know what's going on with the endpoints here? Nope. What's going to be the difference when I plug in -8, do you think? What happens here? I'll have a -1 to a power, and then this power is always what, odd or even? It's always odd, so I'll have -1 to the power, an odd power, which means it's always -1. So that means when I plug in -8, I have the opposite of this sequence right here. So until we figure out what this guy is doing, we can't answer either endpoint. Okay, so we'll come back to that. Your mission is to finish up, let's see, 8 and 9. I will postpone section 10 because we haven't gone over it yet, and then do your best to finish this up and turn it in tomorrow, and we will go over problems 4 and 5 in class. All right, have a good day, do good math.